Alright, in this video demonstration we're going to talk about subnetting. I know your favorite subject matter. I'll give you a scenario 192.168.197.0. Let's say that you need to accommodate 5 networks. First thing I want to do is get my basic chart set up, and we know that binary is a system of 2, and we're going to start off with 1 as a placeholder. This is a representation of either a 1 or a 0 in the binary, so there's really 2 places here. So 2 times 1 is 2. So now we have the ability to put 4 different combinations of numbers in here. So we could do like 0, 0, 0, 1, 1, 0, 1, 1. So that's where it starts getting kind of exponential in the calculation. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Times 2 is 64. Times 2 is 128. And I'm going to stop right here at 8 places. The reason for that is because we're talking about IPv4 octets. There's 4 octets. Oct, you get it? 8. So 1, 2, 3, 4, 5, 6, 7, 8. And there's 8 bits in each octet. The next thing I'm going to do for my chart is add up 128 plus 64, which gives me 192. And this top row that I'm building out here on this chart is going to be a representation of the subnet masks that I can potentially use. So 128 plus 64 is 192. 192 plus 32 is 224. 224 plus 16 is 240. Plus 8 is 248. Plus 4 is 252. Plus 2 is 254. Again, these are subnet masks here. Then I like to draw a box as kind of a placeholder for the default 255s that I will be utilizing for the subnet mask. I identify what class address this is by looking at the first octet. You know that when we're talking about our ranges 1 to 126 is class A, 128 to 191 is class B, 192 to 223 is class C, if we're talking about using classes. 127, if you want to be official, is actually included in the class A address, although it is reserved for loopback. So we see that this is 192 class C. The default class C 255s are 255, 255, 255.0. So this is kind of like a magnifying glass, a microscope of looking at that last 4th octet to get down to zoom in, so to speak, on the bits. This is decimal, and we're going to look at this last octet in the binary. The next thing I want to do is utilize an equation. 2n minus 2 equals. That 2 is a representation of the binary. The n is how many bits we'll be borrowing from this last octet to accommodate for our number of networks that we need to support. And the minus 2 is not using the network number in the broadcast, or the 0 network and the all ones network. Now there is a bit of an issue sometimes with whether or not the configuration that you're using allows for the 0 network to be utilized. It's very simple. Just simply ask someone, hey, can we use the 0 network? A lot of Cisco routers by default support using the 0 network. I teach Microsoft, and typically they do not accommodate or allow for the 0 network to be used. So I will do the 2n minus 2 for both the networks and the host per network. However, if you're in a situation where the 0 network is allowed, then you simply just don't do the minus 2 for the networks. You'll always do the 2n minus 2 for the host per network. So we're going to take an educated guess here and just act like we're borrowing 2 bits and say 2 to the second minus 2. Well, exponentially speaking, 2 times 2 is 4, minus 2 is 2. When I say exponentially speaking, what I mean is I'm not just saying, hey, 2 times 3 is 6. That's 2 times 2 is 4, times 2 is 8, minus 2 is 6 in that scenario. Again, we can't just use 2 to the second minus 2 equals 2. That's not enough. We need to accommodate 5 networks. 6 is what we want to use, so we're going to borrow 3 bits, 2 to the third minus 2, so 1, 2, 3, just putting some placeholders in here. Then I like to draw a box and stop. That box and the information inside that box is going to give us a lot of good information. Now some folks might say, well, John, why couldn't you just borrow 2 to the 4th minus 2? And that will be 14, and that's going to accommodate 5 networks too. Well, you always want to allow for the most hosts per network, leave as many bits left over for the hosts as you possibly can, so you can put as many hosts per network as possible. So we're going to accommodate actually 6 networks. So we're going to have 1 extra network in our back pocket. And we're going to accommodate 30 hosts per network. And the way that I'm getting that number is I see that I have 1, 2, 3, 4, 5 bits left over for hosts in the rest of this octet, and I'm just going to do the same equation. 2 to the 5th minus 2 equals 30. And it's like saying, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, minus 2 is 30. So I'm going to have a total of 6 networks with 30 hosts on each one of those networks. Now all I'm doing here with this chart is just looking at the bit manipulation for the masked off portion of the IP address. So really focusing on these 3 bits. So for example, if I were to say 0, 0, 0, well of course that equals 0, because none of these bits are being turned on if it's 0. 0 is off, 1 is on in binary. If I were to take another combination of 0, 0, 1 and turn this bit on, that's 32. 0, 1, 0 is 64 because I'm turning that bit on and the other 2 off. 0, 1, 1 is 96 because 64 and 32, the 2 bits that I'm turning on, equal to be 96. You see the pattern here. And all I'm doing with this chart is just making life super simple by saying, hey, look, my first network number is 32. And the increments that I'm going in is 32. It's a little bit easier than having to go through this process. Now, should you understand this process, what's going on behind the scenes? Absolutely. But this chart can just make your life a whole lot easier. So we know our first network number is 192.168.197.32. My second network number is 64, 96. Again, I'm going in increments of 32. My last network number is 192. Now I knew that very quickly just by looking at my chart. Just look to the left of the box and I see 192 as my last network number. Go ahead and fill in the holes here. 128, 160. Pretty easy. So here's our 6 networks, 32, 64, 96, 128, 160, 192, all 6 of those. Again, if we were allowing to use the 0 network, well, of course, our first network number, as you see here, would be 0, and the last one would be 224. Again, Microsoft typically does not allow for that in their configuration when you're looking at it. If you're talking about a Cisco box that allows for it, well, it's easy. You've got 8 networks, and 0 is your first one, and 224 is your last one. Easy money. Let's talk about the range here. 33 through 62. Again, 33 is our first host address we can give out on the network, because 32 is the network number, and that cannot be used. So 33 is the first one I can give out, and I'm going to end off at 62 because 63 is my broadcast address that is reserved. All ones, can't be used, and 64 is my network number, next network number. 65 for this range through 94, because 95 would be my broadcast address, which I cannot use. 96 would be the next network number, and you see the pattern here going on down. So 97 through 126. Again, 127 being the broadcast address. Again, 127, just since it's popping up here, is only reserved for loopback when it is in the first octet, and this is not the scenario or case for this. So 127, ironically enough, will be the broadcast address for the 96 network. And you see the pattern going down. I'll go ahead and do the last network of 193 through 222. Again, 223 being the broadcast address, because 224 would be the next network number. And all I'm doing here is saying, hey, 192 plus 32, the increments that we're going in, is 224, minus 2 is 222, making life really easy on us. We can also use this chart to figure out what our subnet mask would be. Haven't already figured it out. 255, 255, 255.224. We can also figure out real quickly what our CIDR notation is, or our shortcut representation of this subnet mask, by just counting up all the contiguous 1 bits through to the box And if we were to take this 255 in the decimal and convert it to binary, it would be 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. I think I got 8 ones there. Same thing for this one, same thing for this one. So we have 24 bits represented here in the box in the binary. If we were to convert these decimal 255s to binary, it'd be 24 ones. Then just keep counting over 25, 26, 27 through to the box. So 255, 255, 255, about 224 can also be represented as /27. Sometimes you might see an IP address maybe written out like this: 192.168.197.40/27. Just an easy way to represent, hey, your IP address is this, and by the way, your subnet mask is that. And if you don't know what in the world that is, then you'll be in trouble, right? So you know this is the /27 is just another way to write out this whole number, and this whole number can also be represented by the /27. So this chart is just really easy, really simple to utilize. For my class, I'm not really concerned if you use this chart or not. It's just an easy way a lot of students have been able to use to conquer the subnetting beast. If you have your own methodology, want to use a different way, have another shortcut, another method, whatever floats your boat, it doesn't matter to me. My main issue is that my students know how to come up with the right answer when they're given a subnetting scenario. And when you go to the field, when you're given a subnetting scenario, real world time, that you know how to come up with the right answer. And that's all that really matters. So I hope this table helps you out and makes your life a whole lot easier when it comes to the world of subnetting. Thanks for watching.